Hello viewers, I am Dr. Mala Das Sharma. Welcome to my channel Chemphilic. Chemphilic is a channel which aims to generate interest in chemistry among the students. Let's start 49th episode of Teaching Chemistry through Riddle. Here is our riddle number 49, which goes like this. X and Y are two different types of reactions. Both are important reactions of halogen compounds. Reagents of same category with slight difference in nature can bring both the reactions. Similarities are found in the mechanistic pathway of both the reactions. In X, hybridization of the carbon atom of the reaction center remains same in the product, whereas alternation of the hybridization occurs in reaction Y. These two reactions are often competitive with each other. At high temperature, reaction X switches over to reaction Y. So this is our riddle number 49. Now let's see the questions. Primary question is, name the reactions X and Y. The answer is X, nucleophilic substitution reaction, Y, elimination reaction. Other questions are, second question, state the characteristics of reaction X. Third question, state the characteristics of reaction Y. Fourth question, substitution and elimination are often compete with each other. Discuss with examples. Fifth question, why at high temperature reaction X switches over to reaction Y? So these are the questions. Now let's discuss the second question. State the characteristics of reaction X. Reaction X is nucleophilic substitution reaction where nucleophile, that is negatively charged species or species with lone pair of electron, attack the positive center, that is positive or partially positive charge of an atom, which is referred as electrophile. This nucleophilic substitution reaction is of two types, SN1 substitution nucleophilic unimolecular, where the leaving group leaves first and then the entering group or nucleophile attack. And second one, nucleophilic substitution bimolecular, that is SN2 substitution nucleophilic bimolecular, where the entering nucleophile attack first and then the leaving group leaves. Now coming to the mechanism of SN1 nucleophilic substitution unimolecular. It is a two-step reaction. What happened initially in the first step, which is the slowest step or rate determining step, it is nothing but the ionization whereby stable carbocation is formed. In the second step, that is first step, that this carbocation is attacked by the base or nucleophile to give the product. Now this is the energy diagram of SN1 reaction. Here this is the transition state and this is the activation energy between these reactants and the transition state or activation energy of the slowest step or rate determining step, whereby carbocation is formed and then from the carbocation product is formed by the attack of the nucleophile. So in the rate determining step, only the substrate, here it is alkyl halide is involved. So the rate is equal to rate constant into concentration of the substrate. Now stereochemistry of SN1 reaction. In SN1 reaction, rate determining step or first step, carbocation is formed. In the carbocation, this carbon atom is sp2 hybridized, which is planar. So this carbocationic carbon atom is attached with the three groups and it is planar, and then the nucleophile can attack from the back side or from the front side. Okay. If the nucleophile attack from the back side, then you will get the inversion product. Suppose the substrate is optically active, chiral center is there. If it attacks from the same side of the leaving group, then you will get the retention product. Initially what happens, this leaving group which leaves this carbon but it does not go far away from it, it present nearby. So this ion pair is formed. When this ion pair is formed, that means positive and leaving negative ion are close by, then the attacking nucleophile can attack only from the back side and you will get the inversion product. Afterwards, when this ion pair breaks, that means this negative ion goes far away, then you will get the free carbocation. In that case, the leaving group can attack either from back side or from front side equally, and we will get the racemic mixture. See the example. This is optically active compound 2-bromo-octane. This is secondary alkyl halide. First step ionization. This carbocation is formed, and then when this carbocation is attacked from the back side of the leaving group, we will get this product, that is plus 2-octanol, and this is the inversion configuration. When it attacks from the front side, we will get the retention configuration. See, inversion configuration is 75%, retention configuration is 25%, because in case of ion pair, this nucleophile can attack only from the back side. Then also you will get the inversion product. And when this carbocation is free, then you will get the racemization, that is retention plus inversion. So overall the product is racemization plus inversion. Therefore inversion product is more, or it is partial racemization. Now factors favoring SN1 reaction. First one is substrate structure. We have seen SN1 reaction proceeds to the formation of the carbocation, and we know the 3 degree carbocation is more stable than 2 degree, then 1 degree, finally methyl. So 3 degree alkyl halide is the most favorable substrate for SN1, then 2 degree, then 1 degree doesn't undergo SN1 reaction. Now nucleophiles in SN1. As in the rate determining step of SN1 reaction, nucleophile is not involved. Therefore, it is not affected by the nucleophile. Okay. See, in this reaction, this X may be chlorine, bromine or iodine, whatever it is, rate will be same. So nucleophile does not have much effect on this rate of the reaction, but it should be a good nucleophile. Weak nucleophile fails to promote SN2 reaction. Therefore, reaction with weak nucleophile also often go with SN1 mechanism if the substrate is secondary or tertiary. Next one is effect of this leaving group. Now, two factors affect the rate of a reaction, that is the ease with which the leaving group dissociates from the carbon atom, ease with which the leaving group is leaving, that means, and the stability of the carbocation that is formed. Remember, the weaker base, those are less tightly bonded with the carbon atom and they can easily leave. Okay. So, weaker bases are beta leaving group. So, stable announce that the weak bases are usually excellent leaving groups and can delocalize charge. So, this iodide is the best leaving group because it's the weakest base among all these halides. Then comes bromide, then chloride, then fluoride. Now fourth point, solvent effect on nucleophile. Here, polar protic solvent. What is protic solvent? Where hydrogen is attached to electronegative atom like oxygen. Polar protic solvents favors SN1 reaction because polar protic solvent can stabilize the cation and anion by solvation. So SN1 reaction is favored by polar protic solvent. Some examples say water, methanol, ethanol, tertiary butanol, acetic acid, etc. Now SN2. SN2 reaction is a single step reaction. The nucleophile attack from the back side of the leaving group. Then one transition state is formed. In the transition state, this carbon atom is sp2 hybridized and the other pz orbital, which is not involved in the hybridization, it holds both the leaving group and the entering group partially. So in the transition state, 5 atoms or groups are attached with this carbon and then the leaving group leaves and you will get the product. So single step, that is the rate determining step. And this is the energy diagram. So from this reactants, this is the transition state, this is the activation energy, and from the transition state directly you will get the product. Now as this both substrate as well as nucleophile or base are involved in the rate determining step. So rate will be equal to K into alkyl halide. Here substrate is alkyl halide and also the concentration of nucleophile. Now the stereochemistry of SN2 reaction. In SN2 reaction, the nucleophile or base should attack from the back side only. It cannot attack from the front side because leaving group has not yet left. So therefore, as it is attacking from the back side and then the transition state is formed, then the final product will have the inversion of the configuration. If this reactant is optically active or chiral center is present, say it is 2-bromo-octane, it is optically active. From here, this is the R product. From here, we will get the S configuration product. And this 100% inversion occurs as the nucleophile has to attack from the backside, and it is known as the Walden inversion. Now factors favoring SN2 reaction. Substrate nature. Here less bulky should stabilize the transition state. Already SN2 in single step, and in the rate determining step or single step 5 atoms or groups are attached to the carbon atom. So the substrate should be less bulky. That only favorable for SN2 reaction. And less bulky means here this methyl halide will be the most reactive, and then primary alkyl halide, then secondary, tertiary will not undergo SN2. Only secondary alkyl halide undergo both SN1 and SN2. So reaction rate increases in this direction. And then leaving groups are same for SN1 and SN2 reaction, that is good leaving groups needs to be stable anion that are weak bases which can delocalize the charge. And here this iodide is the weakest base and most stable base. This is the best leaving group, and fluoride is the strongest base. This is the worst leaving group. Now coming to the nucleophile and solvent. Here strong nucleophile is required because strong base or nucleophile can attack, then it push the leaving group to leave the molecule. That's why strength of the nucleophile or base should be strong, and the polar aprotic solvent favors SN2 reaction. Aprotic solvent means hydrogen is not attached to electronegative atom. Now coming to the consolidated SN1 and SN2. See, for substrate, SN1 prefers the 3-degree alkyl halide, where SN2 methyl or 1 degree. 2-degree alkyl halide can undergo both SN1 and SN2. Then coming to nucleophile, SN1 reaction can occur even with the weak Lewis base or neutral molecule, but strong Lewis base prefer the SN2 reaction, or SN2 reaction favored by strong Lewis base. Solvent for SN1, it is polar protic solvent like alcohol, water, and it will be for SN2 polar aprotic solvent like dimethyl sulfoxide, etc. And the leaving group will be same for both SN1, SN2. Iodide will be better leaving group than bromide, than chloride, than fluoride. Now coming to the third question. State the characteristics of reaction Y. Reaction Y is elimination reaction. In elimination reaction, some fragments are removed from the molecule and multiple bond is formed. See here, this is the halogen atom attached to this carbon atom, which is alpha carbon atom, and next carbon atom is beta. So this halogen and this beta hydrogen removed as HX, and we will get the double bonded compound or pi bonded compound, that is elimination product. Now elimination reaction can proceed in 3 different ways. One is E2, that is elimination bimolecular, E1 elimination unimolecular, E1CB, that is elimination unimolecular conjugate base. Now let's see. Now mechanism of E2 reaction, just like SN2 reaction, here also the base attack this beta hydrogen atom, and then this carbon hydrogen bonded electron pair partially shift here and form the partial double bond, and this carbon halogen bonded electron pair partially shifted to halogen in the transition state. So in the transition state, the base is partially attached to this beta hydrogen, and this leaving group is partially, not completely attached, partially attached to this carbon atom, and partial double bond is formed, and from this transition state directly product, that is alkene, is formed. Now the rate depends on both, that is alkyl halide as well as the base. So rate is equal to K, concentration of alkyl halide and concentration of base. Now this is the energy diagram. This is the energy of the reactant. This is transition state. This is the activation energy. From the transition state directly product is formed. And orientation and reactivity of E2 reaction. If there are two beta hydrogen atoms, that means two beta carbon atoms are there, then the major product will be that one where hydrogen is removed from that carbon atom which contains less number of hydrogen. This is Sedgwick rule. So major product will be according to Sedgwick rule. Hydrogen will be removed from this carbon atom because it contains two hydrogen, that is less number of hydrogen compared to this one. So 2-butene is the major product, 81%, and 1-butene, that is hydrogen removed from this beta carbon atom, that is the minor product. Now coming to the mechanism of E1 reaction. E1 reaction consisting of two steps. Like SN1, here also first step is the ionization and formation of the carbocation, stable carbocation. And the second step, what happened? This base attracts this beta hydrogen atom, and this carbon hydrogen bonded electron pair form a double bond, and alkene is formed as a product. Now, in certain alkyl halides, the carbocation initially formed undergoes rearrangement to form the more stable carbocation, and thus highly the branch chain alkene is formed as major product. See here. So in this molecule, when this ionization occurs, then this carbocation is formed. This is secondary carbocation, and then this methyl group or this alkyl group migrates from here to here. So the carbocation is formed at this carbon atom, which is tertiary carbocation, that is more stable. So it undergoes rearrangement to form the more stable carbocation, and the product is formed as per this tertiary or more stable carbocation. So this product will be obtained. Now, examples of E1 elimination. In this reaction, when heated with sulfuric acid, water is removed and this alkene is formed, and this is the beta carbon atom. So from here beta hydrogen will be removed, and this carbocation is stabilized by resonance participation with both this phenyl group. So it can be readily noticed that the carbocation generated in the first step would be stabilized species due to effective delocalization, that is resonance, promoted by the presence of two phenyl groups on the tertiary carbon. Energy profile of E1 reaction. Here, as it is consisting of two steps, first step is the rate determining step. This is the activation energy of the rate determining step, whereby carbocation is formed, and from the carbocation product is formed. And as in the rate determining step, no nucleophile or base is involved, so rate will be equal to K into concentration of alkyl halide. Now, orientation and reactivity of E1 reaction. For E1 reaction also, it follows when there is a possibility of formation of two products, the major product will be formed according to Sedgwick rule. So here also, this is the more substituted alkene, that is the more stable alkene will form. Okay, this is 82%. And for this E1 reaction, 3 degree haloalkane is most reactive, then 2 degree, then 1 degree. 1 degree doesn't undergo this E1, it follows E2 mechanism. Now E1 CB mechanism. E1 CB mechanism, what happened? Base will, strong base, here we need strong base, it attracts the proton, takes the proton, and then carbon ion is formed. Then from the carbon ion, it forms the double bond here and the leaving group is left. So, this reaction requires substrate which contains groups that can stabilize the carbon ion, that is the presence of electron withdrawing group. Say for example, here these are the electron withdrawing group, chlorine atom and fluorine atom. This is the carbon ion. And then this chlorine chlorine, it attracts the electron density of the carbon-chlorine bond by strong minus I effect. So this negative charge is delocalized. Even because of the presence of fluorine also, this negative charge delocalized and stabilized. And then we'll get this product. So E1 reaction, electron donating ability of the substituents. Okay. And then it should have good leaving group and solvents of high polarity. And these factors favors E1 pathway. Okay. And the base or nucleophile is not important in the rate determining step of E1 like SN1. Now, base is important, or strength of the base is important for E2 mechanism. But because E2 mechanism, you need the strong base. It has to push this leaving group. It attacks the substrate and pushes the leaving group to go away. Therefore, it needs the strong base. And the nature of the leaving group will be same. It should be a weak base. And nature of the solvent will be, it will be the polar aprotic solvents. Okay. If the strong base is used, reaction will move towards E1CB like pathway. Whereas good leaving group with strong ionizing solvent will cause to move towards E1 pathway. Now, fourth question. Substitution and elimination are often compete with each other. Discuss with examples. So, this is the substrate. This is the leaving group. Base or nucleophile. Either it gives the substitution product or it gives the elimination product. Now, increasing the temperature tends to increase elimination reaction due to increase in the disorderliness or entropy. We will discuss this later. Second point. Increasing steric effects at both substrate as well as nucleophile or base tends to increase the elimination. Third point, basicity or nucleophilicity of the attacking species, that is switching from ROH to RO minus. See, ROH is a neutral nucleophile. When it forms alkoxide ion, that is a stronger base, that will increase the amount of elimination. So, now nucleophilic substitution versus elimination reaction. We have taken secondary alkyl halide which can undergo both SN1, SN2 or E1, E2. Okay. When it is treated with aqueous potassium hydroxide, OH minus ion is the base and that is not sterically hindered. That will not offer any steric hindrance. Okay. Then the substitution product is formed. But as soon as you are using alcoholic potassium hydroxide, then potassium ethoxide is formed. That means the base is C2H5O minus, which offers the strong steric hindrance, and then therefore the same alkyl halide, this elimination reaction occurs and the product is the pi bonded compound or multiple bonded compounds. Now, primary carbon electrophile like 1-bromopropane are much more likely to undergo SN2 than elimination, that is E2 mechanism. This is because electrophilic carbon is unhindered and a good target for nucleophile. If it is the primary alkyl halide, then SN2 is preferred because the substrate is totally unhindered. Nucleophile can attack this carbon atom. You will get the SN2 product. And another example, acetate for example, it is a weak base but it is a good nucleophile. And then when it reacts with 2-bromopropane, secondary alkyl halide, then what it happens? It acts as nucleophile. That means you will get the substitution products. Then the strong hindered base such as this tertiary butoxide is strongly hindered. It offers strong steric hindrance. When this base is there, in that case, you will get the elimination product. The bulkiness of the base makes it difficult for the oxygen to reach at the carbon. Because of the bulkiness, it cannot reach to the carbon, and therefore, what happened? In other words, to act as a nucleophile, that means it cannot act as a nucleophile. It is more likely to plug the proton. It takes the proton, which is much more easy for it, and then you will get the elimination product. Now, fifth question. Why at high temperature reaction X switches over to reaction Y? See, when you are increasing the temperature, you are giving the more heat and then more of elimination products obtained. Why? Because at low temperature, activation energy of the substitution reaction is lower than elimination reaction. Okay, and so at low temperature substitution reaction occurs, but high temperature, when more energy is available, it can cross the barrier of the elimination reaction. So elimination occurs. And moreover, in elimination reaction, more number of species are formed. So disorderness increases. This will discuss later also. Disorderness increases. So entropy increases. As entropy increases, this T delta S term, it increases. So minus T delta S, it gives free energy more negative. More, that means reaction will be more spontaneous. So this is the substrate. With base, it can undergo substitution or elimination, but low temperature favors the substitution than elimination. Now, so at low temperature, already I discussed, activation energy of substitution reaction is less. It prefers substitution. High temperature, energy is available. So it crosses the barrier of elimination reaction. So elimination reaction is favored. And if you plot the inverse temperature, with increase in temperature, you see elimination product increases, substitution product decreases. Now, so this is this one. This is the second point. Why at high temperature elimination reaction increases? See here, for substitution reaction product is 2, but for elimination reaction product is 3. That means disorderness increases. Disorderness increases means delta S increases. Already high temperature and then delta S increases. So overall T delta S increases. This is negative. So more of T delta S makes this delta G more negative. More negative means reaction will be more spontaneous. So high temperature reaction or substitution reaction switches over to elimination reaction. So this is all about the substitution and elimination, that is nucleophilic substitution and elimination reaction and their competitive natures. Thank you.